In this video, we are going to compare and contrast different types of network topologies. This video will cover CCNA Objective 1.6, compare and contrast network topologies, and specifically, we're going to take a look at bus, star, mesh, ring, and hybrid topologies. A network topology is just a schematic description of the arrangement of nodes and links that make up a network. There are two types of topologies used to describe networks. There's physical topologies that show the actual geometric or physical layout of the nodes and the links. And then there are logical topologies that show the signal or the data path through the network. The physical topology and the logical topology can be different, and oftentimes they are different. So let's start with the most basic topology, a bus. In the old days of networking, this was the physical topology used by Ethernet networks. Nodes connected by thin net coax cable with a vampire tap to a thick net coax cable that was terminated on each end. And in this type of network, if a host failed, well, it didn't impact any of the other hosts on the network. They could still communicate. However, if the link failed in any section of the link, or maybe something happened to the terminator at the end, then the entire network would go down. On the bus topology, because all the hosts share a common link, only one node can communicate or use the link at any time. This is an example of half-duplex communication. A node can send to receive, but can't do it at the same time, and only one node can be using the link at any one time. If two nodes did happen to transmit frames simultaneously, then what you would have on the network is something called a collision, and when a collision occurs, it disrupts all network communication. And of course, collisions negatively impact network performance. The more nodes that are communicating on a physical bus topology, then the greater the chance of having collisions, and even the number of collisions actually increases as you add more nodes to a bus topology. Also, because of the shared link, all the nodes on a bus network will see the data that's transmitted by any of the other nodes. So what this means, for example, is if host A sends a frame onto the network that's intended for host B, host C and D will also see the frame. Now, hosts C and D will ignore the frame once they see it's not intended for them, because it won't have their MAC address. It'll have the MAC address of host B. But still, it does interrupt host C and D, even if for a few microseconds. Now, you probably won't see a bus network on an Ethernet LAN anymore today, but they are not uncommon in some industrial networks that connect process control devices. Next, we have what's the most popular LAN topology for Ethernet networks, and that's the physical star. In a physical star topology, all the hosts connect using Ethernet cables to a central device such as a hub or a switch. When a host sends a frame on to the network, it goes to the hub or the switch at the center and then is retransmitted by the hub or the switch to the other hosts on the network. Now, the behavior of the network, whether there's a hub or a switch as the central connectivity device, is a little bit different, and we'll go into the differences here in just a moment. Also, strangely enough, because the hub or the switch at the center creates a logical circuit between the hosts, the physical star topology actually ends up operating logically as a bus between two given nodes, and we'll look at some examples in a minute. Let's start with a hub acting as the central connectivity point in a star network. Now, a hub acts like a repeater, and it forwards frames out all interfaces. Just like on a bus topology, when a host like host A transmits a frame, it's going to go to all the other hosts because the hub is just retransmitting it out all of his other interfaces. The MAC address of that frame, in this example, will only match host B. Therefore, all the other hosts, when they receive that frame, will look at the MAC address and say, that's not for me, and they'll ignore and drop the frame, and only host B will accept it, much like the same behavior we saw on the bus network. Now, on a star topology, the failure of the hub or switch in the center of the network means the entire network will come down. However, the failure of an individual host or the failure of an individual link will not impact the rest of the network. So your single point of failure in a star topology is that central connectivity device, whether it's a hub or a switch. A star network with a hub at the center is also using half-duplex communication so that only one host can transmit at a time, and a host can do one or the other. It can transmit or it can receive, but it can't do both. And like the bus topology, simultaneous transmissions will result in a collision. So if host A and host B happen to transmit a frame at the same time, that will cause a collision, and it does temporarily disrupt network communication for every device. Most networks today use a switch at the center of the star topology. And if a switch is used in the star topology, we have full duplex communication, which means not only can a host send and receive at the same time, because the switch is an intelligent device and will only forward frames to the intended recipient based on the MAC address, multiple hosts can communicate at the same time. So here in this example, host A is sending a frame addressed to host B, and the switch forwards that frame to host B, but at the same time, host C is sending a frame addressed to host D, and the switch will forward that frame as well. However, just like when we had a hub, the switch is our single point of failure. If the switch fails, the network will come down, but if a host or a single link fails, that won't impact the rest of the network. In some network designs, redundancy is critical. In some network designs, you can't have a central or single point of failure. You need packets or frames to be able to get from source to destination, regardless if a device or a link fails. A full mesh topology meets that requirement. As you can see from the diagram, in a full mesh topology, there is no central point to the network. There is no central connectivity device. Each of the nodes is connected to every other node for maximum redundancy. If a link fails, traffic can still take an alternate path. For example, if the direct link between host A and B fails, traffic can take another path, such as going through node D. Now, the cost of this redundancy is going to be the cost associated with the increased number of redundant links and the redundant interfaces. There is a simple formula you can use to calculate the number of links required to build a full mesh topology. And the formula, as you see here, is n multiplied by n minus 1 divided by 2, and n represents the number of nodes. So in this example, we have 6 nodes, and if you run 6 through the formula, you'll find you'll need 15 links to connect all those nodes in a full mesh. You won't see desktop computers connected in a full mesh, but the routers and switches and highly redundant parts of the network, such as the network core, may be connected either physically or logically into a full mesh. Now, as I mentioned, the downside to a full mesh to all that redundancy is the cost of all of the links and interfaces on each device. So there's another type of redundant network that is somewhat more cost effective, and that's called a partial mesh. Here, the port and link density is less, which can reduce costs by not having to purchase as many interfaces and circuits between the nodes. Here, we have the same 6 nodes, but because we have a partial mesh, only 11 links are required as compared to the 15 links that we required with the full mesh. If a link goes down between nodes A and B, there are still at least 4 alternate paths. Up next, we have the ring topology, where each node connects to exactly 2 other nodes. One is upstream and the other downstream. Traffic or frames must travel around the ring to each node on its way to the intended recipient. Each node will actually accept the frame and then retransmit it to the next node, going around the ring, in this example, in a clockwise direction. Unless there's some redundancy built in, such as a redundant ring, in other words, a second ring connecting all the devices, then the failure of any node or of a link is going to bring down the whole network. Again, you're not going to see a ring network on an Ethernet LAN today, but some high-speed optical carrier networks such as SONET use ring topology. And finally, there's the hybrid topology. This type of topology incorporates multiple types of other topologies connected together to create a more complex hierarchical network design. In this example, we have a full mesh topology used at the core of the network, and that is providing redundancy while we have 2 star topology networks connecting LAN hosts. And we also have a ring topology network that may be connecting perhaps multiple sites in this particular organization. Most large enterprises use network topologies with this type of hybrid and hierarchical design.